So we have finally neared the end of this section and actually this chapter. And today we are going to see a special transformation. We have already applied transformations on homogeneous and Bernoulli equations to reduce them to types which can be easily solved. And today we are going to see a special type of equation, and let's see what type of transformation we can apply on that. It comes in the form of this theorem 2-7. And this is the equation that we are going to consider. a1x plus b1y plus c1 times dx plus a2x plus b2y plus c2 times dy equals 0. So you can see that unless special values of this a, b and c's are given, this is neither linear nor homogeneous. It's a new type of equation. First order, but still a new type, where these coefficients are of course constants. Now two cases arise. If a2 divided by a1 is not equal to b2 divided by b1, then we apply the following transformation to the original differential equation. Small x equals this is a new variable, capital X plus h, and small y equals capital Y plus k. What are these h and k? This h comma k is the solution of the following system. a1x plus b1y plus c1 equals 0 and a2x plus b2y plus c2 equals 0. If you look carefully, this is just the condition for these two equations to have a solution, and then it will have a unique solution. That is why the author says is the solution. So if we apply this transformation to the original differential equation, then it gets turned into this homogeneous equation. a1x plus b1y dx plus a2x plus b2y dy equal to 0 in the new variables capital X and capital Y. And this is case 2. If a2 divided by a1 this time is equal to b2 divided by b1, then a name has been given to it, k. Then the transformation z equal to a1x plus b1y. Now we are introducing this new variable z, which is this. Reduces the original differential equation to this time a separable equation in the variables x and z, and then we can solve it. To illustrate its use, let's consider this example 219, where the equation is x minus 2y plus 1 times dx and 4x minus 3y minus 6 times dy equal to 0. So in the solution we don't write sentences, okay, we just do the main calculation. Here a1 is 1, b1 is minus 2, because for our theorem we do not need to identify c1, so we do not write that. Similarly, we only need a2 and b2, which are respectively 4 and minus 3. Okay. Now a2 divided by a1 is 4 divided by 1, that is 4. And b2 divided by b1 is minus 3 divided by minus 2, that is 3 divided by 2. So they are not equal, which means that these two equations obtained by equating this and this to 0, this system has a unique solution, and that solution is 3, 2, which you can check. So this should be our transformation. We said transformation because the transformation includes both these things. X equals x plus 3 and y equals y plus 2. So you just simply substitute these things in this equation. In place of x, you write x plus 3, and in place of y, you write y plus 2. Okay, so x plus 3 minus 2 times y plus 2 plus 1 times d. Do not forget to write x plus 3 here as well. Okay, differential of x plus 3 plus 4 times x plus 3 minus 3 times y plus 2 minus 6 times differential of y plus 2, that is equal to 0. And after simplification, this becomes this. You can check that we no longer have any constant term. For example, here you have 3 plus 1, which is 4, and minus 2 times 2 is minus 4. So they cancel out, and we are only left with capital X minus 2 times capital Y. That times dx, because d of x plus 3 is d of x plus d of 3. 3 is constant, so d of 3 is 0. So this becomes dx. Similarly, this part becomes 4x minus 3y dy equal to 0. All the capital variables. And now you can clearly see that this is the homogeneous equation, which you can solve using your usual method for solving homogeneous equations. You find a solution in the new variables capital X and capital Y, and then you bring back the old variables using reverse transformation. In place of capital X, you write small x minus 3, and in place of capital Y, you write small y minus 2. So that part you can do it yourself. And next we have example 220. Here the equation is x plus 2y plus 3 times dx plus 2x plus 4y minus 1 times dy equal to 0. As we will see here, case 2 will be used. So in this case, a1 is 1, b1 is 2, a2 is 2 and b2 is 4. And you can check that both a2 divided by a1 and b2 divided by b1 are equal to 2. So the transformation we need here is z equal to x plus 2y. This part, you forget the constant part, you only consider this part, x plus 2y. Actually, you can also consider 2x plus 4y, nothing will essentially change. You just note that this is twice of that, and that is 1/2 of this. That's the only difference. So now how does the equation get transformed? This is z, so z plus 3 dx remains as it is, plus 2 times z minus 1, and then in place of dy we are going to write, well actually in place of y itself we write z minus x divided by 2, and then using properties of differential that becomes dz minus dx divided by 2, and then when you rearrange things, this is what you get, 7 dx plus 2z minus 1 dz equal to 0. So you can clearly see that this is a separable equation which you can just simply integrate. Solve this and then bring back y. Okay, you get rid of z by bringing back y, and that will give you a family of solutions. And finally, the author concludes by saying that there are many extremely special types of first order differential equations which have methods available for their exact solutions. Exact solutions exist for them, and there are methods for finding those solutions. We are, however, not going to go into a detailed study of them, and we stop here itself in this chapter. He, however, mentions this German book which has many such methods. I am not going to try to pronounce this and butcher the name, okay? That's disrespectful. You can see it for yourself. So in the next video we will solve some exercises, and then we will move on to the, not in the next video, but after that we will move on to the next chapter where we will use these methods to solve some problems mainly from physics, but from other disciplines also, I think.